only to Alma. Okay? So this gives you an idea of why we look at these things. And stuff like that. And here's this idea of connectedness. So you have different telescopes around the world. We have one in South America. And the reason why the South American one, the South Pole rather, is so interesting is because the air is so cold, hot air carries moisture. The colder the air is, the less moisture it's able to carry, right? It saturates sooner. So at the South Pole, it's so cold, it's always below -40. Therefore, the atmosphere here looks like it's at a higher altitude because it has less moisture in it. So this is a desert. You may not believe this, but the South Pole is a desert. It snows it doesn't rain very much, a little bit of precipitation. It's mostly blowing snow. Okay? Extremely cold. And here is the site. So here's the South Pole, here's Alma, here's Kilimanjaro, here's Europe. And that would create 4 antennas which would help us to get very high resolution and then help one guy win a Nobel Prize for looking at a black hole at the center of the universe, our galaxy. And myself and Jiwaji, we will get a stale piece of cake sent to us in the mail from the guy's Nobel Prize party. We will get nothing. We won't even be recognized, but we'll get a piece of cake. Okay? And we don't worry about that. We just want to do some good science. So I'm going to just talk a bit about the science. I'm going to actually talk about my science. Because other people's science I find boring, so I'm going to talk about my own. No, I'm joking. So this is a star-forming region. This is called the Cat's Paw Nebula. And it looks kind of like a cat. You see the hand, the paw. Okay, in there, right in here, is massive stars being born. When I say massive, I mean stars that are 5 or 10 or 20 times bigger than our sun. And they're born exactly like raindrops in the sky. They condense, they start spinning, they do funny things. The only difference is they're in zero gravity. Okay? So that's the Cat's Paw Nebula. So if she has a kitten, I call it Kitty. And what is this showing? Okay, here we go. Okay, so, and the one thing I have to tell you about astronomy is you're really a detective. You're actually not, you have to, because think about it. If I put this glass of water, if I hid it down here, can you see that glass of water? That bottle of water? Can you see it? Can you see it? No? You can barely see it, right? That's astronomy. Astronomy, everything is hidden. So in astronomy, here's the glass. If I can look at it, you all can identify this as a bottle of water. What if the bottle of water is behind this chair? Can you see it? No. So how do you know I have a bottle of water back here? You have to take my word for it, which would be really bad. Don't ever trust me. I'm an astronomer. Don't trust astronomers. That's very bad. Anyways, but the point is that in astronomy, you spend your life getting one data point. So you'll see that the chair is moving slightly, somehow. And from that little piece of information, I have to imagine that there's something behind it. There's something behind the cloud. So I look through clouds and I use things called masers, which are basically laser beams in space. So what I do is I tune my telescope to frequencies where you get lasering effects. The masers, like a molecule like hydroxyl, will have various transitions that will get overpopulated, and then something will trigger the population to depopulate, and you'll get a laser beam. And we call them masers, for microwave amplification, okay? Same principle, exactly the same. In fact, the reason why they found masers is because they were thinking of the idea of lasers. And initially, they thought they had discovered a whole new molecule called mysterium. But in fact, it was just a lasing effect in hydroxyl. So all of these lines over here are transitions in hydroxyl. So this is a hydroxyl, an OH molecule, okay? So the ground state at 1665, here's an excited OH line at 6030 megahertz, 6035 megahertz. So we literally tune our telescope to 6035 megahertz, and then we look at the Doppler shift. So if the laser beam is moving towards you, it's blue shifted. If it's moving away from you, it's red shifted. So blue shifted is this way, red shifted is that way. Now, the interesting thing, I was looking at, I told you, I have to be a detective. I was looking at this line here, 60-30, and I found this maser in, I don't know, it was in 2014, and no big deal, nothing exciting. I would not even be able to, even I wouldn't publish that. Not exciting. Okay, it's there. But 6 months later, this component turned on. And it made me realize something interesting had happened. And I thought to myself, I should monitor this source. And I realized I had been already monitoring this source. I'd already been looking at it at other transitions, because we have a very long-term 20-year monitoring program that we were doing towards various stars. This was one of them. So the cat's paw, we actually were looking at the water, the methanol, and the ground state OH. And so what you see over long periods of time, this went, you can't tell, it's a crappy diagram, that's 300, that's 3,000. So the water went up by a factor of 10 at the exact same time that this line turned on. Now the exciting thing about this is I have three molecules, hydroxyl, water, and methanol. All three have components, laser beams, that turned on at exactly the same time. Look here. Very little, this. Nothing, this. Okay? That has never been seen before. Okay? So basically, this is Kitty. This is the star forming region being born. This is called Kitty. I call it the Christmas tree effect, because no one has ever seen so many transitions turn on at the same time. Normally you get one, maybe two, and they flare, they do funny things. Everything's variable. Everything in the universe is variable, by the way. I actually monitor 12 transitions. I have 15 actually, but only 10 of them flare. Okay, so now I can create a light curve. A light curve is just the peak. So if I take the peak right here, and I plot that peak, and I measure it every day, then I can create a light curve. Velocity, the peak versus time. And I can show you that. Next. And here is the components turning on. So here's hydroxyl turned on, methanol turned on, methanol turned on, water turned on. These guys I only started monitoring after the peak. So this is the peak right here, here and here. And they're dying away. Okay? So basically, I can use my long-term monitoring program to determine when Kitty was born. Kitty was born on the 13th of January, 2015. I'm the first person that can tell you a birth date of a star. Because we monitor, we were able to measure that, and now we can publish it. This will get published, by the way. Unlike my last paper that got rejected, this will be published. The more interesting thing to me is that the physics is all crazy. It doesn't make sense to see these types of masers together, because one is caused by shocked gas and the other is caused by radiation. So even the theory is wrong. So remember what I said to you about theory and observation? Well, in this case, now observation is leading. Nobody can explain these things. Okay? And lucky for me, some Americans were re-observing the millimeter, which is what we're going to do with a telescope on Kilimanjaro. They were re-observing exactly, this is really quite entertaining, let me go back one, at the peak. Here's the peak, happened on the 15th of August, okay? The Americans were using ALMA in the Atacama Desert, and they made this picture here on exactly the 15th of August. So we just got lucky. And this spot right here was 60 times brighter than what it was seen 10 years before. Now, their idea of monitoring and mine are very different. They look at observations every 5 or 10 years. Okay? Me, I look at it every 2 weeks. So, because I got observing time. I got a simple telescope. Okay? But irrespective, that is new. And Kitty, all of this stuff, this is methanol. 1, 2, 3. There they are there. This was done in 1996. Here they are. 1, 2, 3. 1, 2, 3. That is the original star forming region. This is all new. Okay? There's nothing up here. Okay? So, and there's no radio. There's no radio. There's no dust. There's no nothing. This and this are associated. This area here. So basically what probably happened was we had two protostellar objects about the size of 2 or 3 solar masses, 2 or 3 times the sun, and they merged. When they merge, they give off a massive explosion of energy, radiation, which led to the outburst of energy that heated the dust and turned on all my masers and caused the Christmas tree effect. So I have to prove that. So as I said to you, it's detective work. I first thought I found something interesting. I monitored it. Somebody else looked at it. Then I did these are VLBI observations. This is very long interferometry between Australian and South African telescopes. Okay? So again, high resolution, ultra high resolution. These are milliarc seconds. So that's 1,000 milliarc seconds. So that's 1 arc second is that big. So the resolution is very high because of the baseline width. And that's star formation. But this, I don't even know what this is. So I discovered this just 2-3 days before I flew here. And I can't even explain to anybody, not even myself, what I'm looking at. I've contacted my friends in America, and none of us know why this is there. So what we've seen here is this is the days of the year. So this is day 6,000, day 6,500. Right now it's probably day 7,800, okay? So today is probably 7,800, okay? And I'm counting from the year 1901. That's why it looks funny, but that's what it is. So I started observing 5 years ago, and you can see here, it's starting to rise while this one is falling. So it's anti-correlated. It's out of phase by 180 degrees. I can't explain that. I don't know how to explain that. And to me, to be honest with you, we could literally be looking at aliens talking to us, for all I know. No, I mean, and you know, as I said to you, we are like Sherlock Holmes. We're detectives. We have to write down all of the possibilities, and then we just systematically strike them off when we've proven them to be incorrect. Okay? But make no mistake, we are detectives. Astronomers look for things, and we try to find it based on very limited knowledge. If you get a fingerprint, I might be able to prove that you stole my wallet, right? Same idea. So I can't even explain this. I don't know how to explain this. It might be instrumental, it might be part of the artifact of how I observe, but it also could be aliens. I doubt that. It's probably rotating stars going around each other, and they cause it to turn on and off, on and off. And that's all it is. One turns on, the other one turns off. Very simple. But that's never been seen before either. So Kitty was born, and that's happened. And let's see what else we got here. And so these are other examples, just pretty pictures I wanted to show. Here is a galaxy, M51, and you can see the contours of the millimeter, made by a single-dish millimeter telescope, and Hubble is the optical. And then over here, you can see the red is the neutral hydrogen. This is CO2, or CO, carbon monoxide. And then the optical is in blue. And just to give you some idea of how astronomy works, you use one telescope, then the next, then the next. Anyways, and that's the story of that. But the reason why people want to build a telescope on Kilimanjaro is because of this telescope, the Event Horizon Telescope. They need a telescope in southern Africa so they can look at the black hole. This is a simulation of what the black hole will look like if you have a telescope in Namibia. So it looks like that, okay? So they actually are seeing the shadow of a black hole, and they think that's going to win them a Nobel Prize and give Jiwaji and I a piece of stale cake. So I'm waiting for my piece of stale cake. I don't know. It's not really exciting. And that's not my science, but that's what they're trying to do. They're trying to find a black hole at the middle of a galaxy. You don't build a telescope to find one detection. You build a telescope for things we don't know. Remember what I said, forget the scientific method. We design telescopes for what we don't know, not what we do know. We need to design telescopes, we need to be smarter. We need to design things that we can do. We can just invent ideas, and we can go out there and go on a fishing expedition and literally look for something new and interesting. And remember, astronomy is cold temperature physics. Everything I look at is only hundreds of degrees Kelvin or less. So some of these objects, like this area here, will literally be 50 Kelvin, 15 degrees above absolute zero, okay? And they'll have densities of 1,000 particles per cubic centimeter, right? Not like we have moles per cubic centimeters, a particle per cubic centimeter. So we have very interesting laboratories in astronomy. So we don't want to design a telescope for one experiment. We want to design it to do anything that any of you can dream of. And that's very important. So this is what I always say. So basically, that is the end of my talk. I hope it was coherent. I hope I didn't ramble too much. And I'll hand it over for questions. Thank you. I have 11 brothers. I can sell you some, okay? I grew up with 11 brothers in a small village. Something I didn't tell you, that when I went into astronomy, like most of you, I grew up in, I don't know, most people around it, did most people here grow up in villages, like small villages or out in the countryside? I grew up in a village of 300 people, and my family was 14 children, okay? No running water, none of that stuff. And I had nobody to tell me what an astronomer was. I saw them walk on the moon in 1969, and I wanted to be an astronaut. I had no idea what it meant to be an astronaut. I'm standing here today because Neil Armstrong stepped on the moon at 10:56 p.m. Sunday, July 20, 1969. I know exactly the date